This is slide number 28 and I am your presenter Asloob Mudassar. Before that we have discussed the Fourier transform of the rectangular function abbreviated as rect function. Now we are going to calculate the Fourier transform of the circular function which is abbreviated as a circ function. The function circ has a circular symmetry and it depends only on a single variable r and is independent of the azimuth variable theta. For objects which are separable in polar coordinates and have circular symmetry can simply be expressed as. So here we have O as a function of r and theta, the space coordinates r and theta in the polar coordinates, and we can split this small o into two functions. One is O subscripted to capital R and is a function of r. The other is O subscripted to capital theta and as a function of small theta. So you see that we have separated this small o into two, O capital R and O capital theta. Now we are assuming over here that O subscripted to capital theta is independent of the value of small theta, which we have written in the third expression, and here in the fourth expression we can drop small o subscripted to capital theta because this is constant, and this constant will not make any changes to the Fourier transform that we shall calculate for the object O. The circ function in the Cartesian coordinates is given by circ of r is equal to circ of square root of x square plus y square and is not separable into x and y variables. We cannot separate the circ function in when we are working in the Cartesian domain. So we have to work out the Fourier transform of the circ function in the Fourier domain. Now let's recall some variables. X and y are the variables in the Cartesian coordinates in space domain, and fx and fy are the corresponding Cartesian coordinates in the Fourier domain, and r and theta are the coordinates in the polar domain for the polar coordinates in the space domain, and rho and phi are the polar coordinates in the Fourier domain. So we have mentioned the Cartesian coordinates, we have mentioned the space variables in the Cartesian coordinates, the space variable in the polar coordinates, and we have also mentioned the Fourier domain, Fourier coordinates in the Cartesian system, and we have also mentioned the Fourier variables in the polar domain, which is rho and phi. Let's write down the relationship between the space domain variables in the two coordinate systems and also the relationship between their Fourier domain variables. So what is the link between these variables? This is depicted over here in this slide. Relationship between space domain variables. X is equal to r cos of theta, y is equal to r sin of theta. So you see that we are relating the two space variables, and where r is equal to the square root of x square plus y square and theta is equal to tan inverse of y over x. So we have both relationships, that is we can find if r and theta are known, we can calculate x and y, and if x and y are known, we can also calculate r and theta. Now you know that in the Fourier domain variables we can similarly write down the relationships, and these are fx is equal to rho cos phi, fy is equal to rho sin phi, where rho is equal to square root of fx square plus fy square, and phi is equal to tan inverse of fy over fx. So similarly, if you have rho and phi, you can find out fx and fy, and similarly if you are given fx and fy, you can compute the value of rho and phi from these expressions. For circularly symmetric objects, the Fourier transform is implemented through Bessel Fourier transform denoted as capital B. You know that in the Cartesian coordinates we use the Fourier operator tau, which we have shown in the second line over here, and but in the Fourier transform for the circular functions we shall be using the Bessel Fourier transform denoted as capital B. This is what we have done so that we can make a distinction that when we are talking about when we are writing B, it means that we are writing B for the objects which are circular symmetric. So in order to transform the Fourier integral from the Cartesian to the polar coordinate systems, we shall make these three transformations. That is, dx into dy will be replaced as by the segment r into dr into d theta. The Fourier operator tau type of Fourier operator will be replaced by the Bessel operator capital B, and the Fourier transform of the object, which is capital O, as a function of fx and fy will be replaced by capital O subscripted to p as a function of rho and phi, and p stands for the polar coordinate systems. So you see that making these changes we can convert our Fourier integral in the Cartesian coordinates to the Fourier integral in the polar coordinate systems. If an object is expressible in polar coordinates and has a circular symmetry, then such an object has a Fourier transform which also has a circular symmetry. So if object is a circular symmetry, if object has a circular symmetry, then its Fourier transform will also have the circular symmetry. Now we are using a circular symmetric function, that is capital O subscripted to p as a function of rho and phi will be equivalently replaced by capital O subscripted to p and as a function of rho only. So it has no dependence on phi, so we can say that it has a circular symmetry in the polar coordinate systems. In the polar coordinate systems for the Fourier variables. Okay, now let's transform the Fourier integral in the Cartesian coordinate systems given in the first row and to the polar coordinate, to the Fourier transform in the polar coordinate systems. And the transformations over here that we have given, we are using these transformations over here in this integral on the right hand side. And after making these transformations, we have two parts of this integral. One is with the limit from 0 to 2 pi as with the variable theta, and the other from or over the variable r, which has the limits from 0 to infinity. And you see that these two integrals are not separable into theta and r coordinates, because look at the exponential factor, which is e to the power minus iota 2 pi r rho. Here you know that we have r and rho both are appearing as an argument of the exponential functions, so we cannot separate r and rho. So that's why we cannot write separate integrals depending upon the variables of theta and the separate variables depending upon the variable r. Okay, now we have further simplified the results given in the row number 3, and here we are going to introduce a function which is called J naught, that is a Bessel function of a first kind order 0. So it has an argument 2 pi r rho, and then you know that we have this integral which is the integral over the variable r. Now this integral has no dependence, has no explicit dependence upon the variable phi, upon the variable theta. So it has an explicit dependence only on the variable r. So you see that here you can see that in the fourth row that we have written down the integral, it has limits from 0 to infinity, it has a variable r, it has the radial part of the object which is O subscripted to capital R, and as a function of r multiplied by the Bessel function J0, which is a Bessel function of a first kind order 0, and the argument of that is 2 pi r rho, and the integration variable is r. So we abbreviate this whole integral by this one, that is, it is capital O subscripted to capital P and as a function of rho. So whenever we write capital O subscripted to P as a function of rho, we shall write down this integral, that is 2 pi integration for limits from 0 to infinity, integration with respect to variable r, and the integrands are r, O subscripted to capital R, and J subscripted to 0 with an argument of 2 pi r and rho. So J naught is the Bessel function of a first kind and order 0. So here we have given the definition of J naught separately, although we have introduced J naught previously, but now we are giving its separate definitions, that J naught of 2 pi r rho is equal to 1 over 2 pi, the limits from 0 to 2 pi, and over here we have the integration with respect to theta, and in the exponent we have e to the power minus iota 2 pi r rho cos of theta minus phi. So you see that this J naught has an explicit dependence upon the variable theta and an implicit dependence upon the variable r. So if r and rho are known, we can compute these integrals, but if any one of them is unknown, we cannot compute the integrals. Okay, now we are going to talk about, you see that before that we have, for example, up to this point, we have talked about the circularly symmetric object in which the object has only radial dependence, and the other part, which is the azimuthal part, for example over here, was constant, and there we have missed that part and did not include. Again, you can see over here in this line we have only the radial part, but you know that if we don't have the radial dependence only, but if we have a dependence on the other variable also, then we need to use another transform, which we call it as the Hankel transform. So Fourier transform in polar coordinates is defined by when the function is not dependent. So you see that here, you look at this one, the definition of the Hankel transform of order k in terms of the Bessel function of a first kind order k is given by, this is the Hankel function that we have, h subscript to k, and operating on the radial part of the variable or on the radial part of the object O, which is O subscript to capital R and the function of R. On the right hand side we have the integral, in which we have defined the Hankel function on the radial part, which is equal to 2 pi integration from 0 to infinity, and the integrand is R O, capital O subscript to capital R of depending upon the variable R, and the first the jk, which is the Bessel function of a first kind order k, and with an argument of 2 pi r rho with respect, and the integration is with respect to variable R. So this is what we have shown the Hankel transform, because we shall using the Hankel transform in the Fourier transform of an object, which we have shown over here. The object has dependence on the radial part and also as well as on the azimuthal part, because here we are not taking O subscript to capital theta as a function of theta. This is not constant. So in such a case we have to use somewhere the Hankel transform, which we are given in the next one. So separation into radial and azimuthal part, this we can separate the radial part and the azimuthal part, but we are not treating here that the azimuthal part is constant, but the over object O, which is a function of R and theta, is also depending upon the radial part as well as on the azimuthal part. That is, O as a function of R and theta is not circularly symmetric. So such a function, the Fourier transform of such a function is given over here. That is, the Fourier transform in polar coordinates is defined as, so here we are talking about capital O subscript to p as a function of rho and phi. Now you see that here we have two variables, rho and phi. It means that before that we had only rho, now we have two variables. It means that over a function over here, for example the Fourier transform, we have subscripted to p, which means that we are talking about the Fourier transform in polar coordinates of an object O, small o, which is a function of R and theta, and its Fourier transform, you know, that is given by this whole expression stands for the Fourier transform of an object, of a polar object which has a radial dependence as well as the azimuthal dependence, and the radial dependence is depicted in the Hankel transform, which is given. So let's read it. This is a summation sign from k is equal to minus infinity to plus infinity minus iota raised to power k e to the power iota k phi, and then we have the Hankel transform of order k operating on the radial part of this function, which is O subscript to capital R as a function of R. And then we have the azimuthal dependence, the integral on the azimuthal part, which is 1 over 2 pi from 0 to 2 pi, and the integral variables is theta, and the integrand are small o subscript to capital theta as a function of theta multiplied by e to the power minus a minus iota k theta. So this is, you know, that the Fourier transform, full expression of the Fourier transform when the polar coordinate has no circular symmetry. Where tau subscript to p is actually a Fourier transform operator in the polar coordinate systems. Okay, now the Fourier transform of the circ function. Let's calculate the Fourier transform of the circ function. This is given by, you know, that capital O subscript to p as a function of rho and phi will be represented by Bessel function, because if any object has a circular symmetry, we shall be using the Bessel function in to identify that the object has a circular symmetry. So this B is operating on O, which is an object having dependence on r and theta, but only the radial part will be important, because this function O is independent of the value of the theta, that is, it has no dependence on the azimuthal part. So B is now operating on the circ of r, which is given by 2 pi for integral from 0 to infinity. The integrand is r multiplied by the circ of r multiplied by the j naught with an argument of 2 pi r rho, and the integration variable is r. So we can simply write this integral as in this line, that O subscripted to P stands for the polar Fourier transform in polar coordinate as a function of rho. Now you see that we have dropped over here the phi. Here we have used phi, but here we have dropped the variable phi, because over Fourier transform will also be circular symmetric and would not depend upon the variable phi. So this is equal to Bessel function of the circ function, and then we have 2 pi integration limits from 0 to 1 r, integrand is r multiplied by the Bessel function of order first kind order 0, and the argument is 2 pi r rho, and the integration variable is r. So you see that this is give you, so if you evaluate this integral, you can get the Fourier transform of the circ function. Now we have, okay, the picture ends over here, but you know that we want to represent this circ function in more useful form. For example, when we were talking about the Fourier transform of the rect function, we wanted to convert it into, we wrote down there the more useful form of the rect function, which was a sinc function. Now similarly, we want to use the Fourier transform of the circ function into something more useful form. For that we are going to use the substitutions. This is what in the last row, for example, here we have given the substitution that r is equal to r prime over 2 pi rho, and dr is equal to dr prime over 2 pi rho, and the limits that we have calculated from 0 to 1 will be replaced by from 0 to 2 pi rho, and the integrands will be replaced by r will be replaced by r prime over 2 pi rho, and over here j naught will be replaced by r prime, because 2 pi r rho will be replaced by r prime, and here dr will be replaced by dr prime over 2 pi rho. So these are the substitutions that we have made, and at the same time we have shown these substitutions explicitly in the last row. Okay, now let's go one step ahead, and then you see that this is a Fourier transform of the as a function of rho. So we have shown the Bessel function of a circular circ function, and then you know that we have shown it in modified variables, and you can see that it is equal to 1 over 2 pi rho square, and multiplied by the integral from 0 to 2 pi rho. Integrand is r prime, j naught r prime, and dr prime. And this integral has been defined as jinc of rho. So you see that this jinc of rho is very important function. It is very much similar to the sinc of rho, because but jinc of rho, you know, that has similar characteristics, and we shall be talking about sinc of rho and jinc of rho repeatedly and many times in the rest of the Fourier optics course. So remember this jinc function and its mathematical expression, very important. Okay, now we have explicitly shown these results over here. That is the Fourier transform O capital O subscript to P as a function of rho is equal to Bessel Fourier transform of the circ function is equal to J1 of 2 pi rho over rho will be equal to the jink of rho. So jink of rho in terms of the Bessel function of a first kind is also given, that is J1 of 2 pi rho over rho. Remember that when we are talking about the sinc function, we related the sinc function with the sign of something, you know that. Recall the previous slides and you will find out the relationship of the sinc. Here we have the jink of rho related with the Bessel function of a first kind of order 1 as 2 pi rho over rho, where J1 of 2 pi rho is equal to 1 over 2 pi rho, integration limit from 0 to 2 pi rho, and integrand is r prime J naught of r prime and dr prime. And jink of rho on the left hand side we have defined it as J1 of 2 pi rho over rho. Okay, in Cartesian form, let's represent this the Fourier transform of the circ function. Over here, look at. So this is the Fourier transform of the circ function, but if we write the r in terms of the Cartesian coordinates, we can replace right by the square root of x square and y square. So the Fourier transform operator, since we are working in the Cartesian coordinates, we are replacing b by the this tau type operator, which is the Fourier operator we have been using for the Cartesian coordinates. Now this is equal to the jink, as we have evaluated earlier, that the Fourier transform of the circ function is actually a jink function, but jink rho, the rho will now be replaced by the Cartesian coordinates in Fourier domain. So rho will be replaced by square root of fx square plus fy square, and that is equal to related with the another expression, which is J1 over 2 pi rho will be replaced by the square root of fx square plus fy square and divided by the same term, that is the square root of fx square plus fy square. So you see that we have given the Fourier transform of the circ function in polar coordinates as well as in Cartesian coordinates. Now what we are going to do next is that we are going to plot this function. That is, we are going to plot the circ function. And here we are here we are going to define circ of r over r naught. Before that we have been talking about the circ of r only, which means that r naught was equal to 1 there. And now we are going to define the circ function. More accurate form of the circ function is r over r naught, which is equal to 1 when r is less than equal to r naught, because the radius of this function circ function is r naught. Before that the radius of r naught was equal to 1, and now this circ function is equal to 1 when r is less than equal to r naught and is equal to 0 otherwise. So in a radius of r naught, the circ function is equal to 1, and beyond that the circ function will be equal to 0. Now let's plot this function. Here we are talking the Fourier transform of the circ function of r over r naught, and you see that before that we have worked out the Bessel function of the circ function of r only. Now we are going to give the expression of the Bessel function of the circ function of r over r naught. Now r naught is also present in the denominator. So you see that we are multiplying, we are actually generalizing from the previous Fourier transform, that it is equal to J1 of 2 pi r naught rho. Before that r naught was equal to 1, but now the r naught is present. So we have 2 pi r naught rho and divided by r naught rho. Now if we plot this circ function, which is in principle a jink function, that is J1 of this argument divided by J1 of 2 pi r naught rho over r naught rho is actually a jink function. Let's plot this function for the value of r naught is equal to 7 arbitrary unit. So if we plug in the value of r naught is equal to 7 arbitrary unit in the circ function in the Fourier transform, which is J1 of that one over r naught rho, and if we plot plot the value of rho on both on this side, because rho is circular symmetric, because this is a circular symmetric function, so rho, the value of rho will be effective in all directions. So look at this picture on the right hand side. So you have the three-dimensional picture of this one. You can see that there is a main lobe in the center, and you can also see some side lobes or some ringing effects at the bottom of this main lobe. These are actually may be regarded as the side lobes, and in the zinc function the side lobes are all positive, whereas in the zinc function the side lobes varies from positive value to the negative values. So this main lobe is also is the whole positive, and of course these side lobes are also positive, and the one-dimensional cross section is what we have shown over here. Look at the one-dimensional cross section. The main lobe is very broad, and you can see that very small amount of side lobes are also visible in this picture. Again, the main lobe will control the resolution of the imaging system, and the side lobes will control the contrast of the images in an imaging system. And the size of this two-dimensional picture is 220 pixels by 220 pixels. Okay, now the thing is, what can we calculate the inverse Fourier transform? For example, yes, we are now going to give the inverse Fourier transform expression for the first time for the Cartesian coordinate systems and also for the polar coordinate systems which has a circular symmetry. So look at this first line. Now we have small object O on the left hand side as a function of variables x and y, and you know that we have this inverse Fourier operator which is tau to the power -1. This is called inverse Fourier transform operator operating on capital O with Fourier variables fx and fy. So the inverse Fourier transform should always operate on the Fourier domain variables and will give you the answer in the space domain variables. So on the right hand side we have the integral. You can see that this integral is very much similar to the integral for the Fourier transform, but this is for the inverse Fourier transform. Now the difference is that difference is that we have plugged in over here the value of capital O, which is actually the Fourier transform as a function of fx and fy. And now another difference is that we have used the positive sign over here, e to the power plus iota 2 pi, within the bracket we have fx into x plus fy into y. So we have a positive sign over here, but in the Fourier transform we have the negative sign. In the inverse Fourier transform we have the positive sign over here. And you see that there is another change, that this integration will be carried out with respect to the variables fx and fy. Before that, in the Fourier transform we calculate the integral with respect to the variables dx and dy. Here we calculate the integration with respect to the Fourier variables dfx and dfy. And now let's look at the inverse of the Fourier transform in the polar coordinate system having circular symmetry. So look at this small o subscript to capital R as a function of R is equal to, here we are using Bessel inverse operating on capital O subscripted to P as a function of rho, because rho is only the variable that we are using. We are not using phi. It means that we are talking about the polar coordinate systems having circular symmetry. Now it is given by the integral 2 pi into integration from 0 to infinity. The variables of the integration is rho, and the integrand is rho multiplied by capital O subscripted to P as a function of rho, and multiplied by the Bessel function of first kind order 0, that is J0 as a function of 2 pi r rho. So where capital O subscript to P as a function of rho is a function defined at the Fourier plane and has a circular symmetry. So this is because the object has a circular symmetry, so the Fourier transform of this one has also circular symmetry. So you see that we have given here the definitions of the forward Fourier transform, the inverse Fourier transform in both Cartesian coordinates and in the polar coordinates system, especially the polar coordinate system having circular symmetry, because such an objects are frequently used in optics. So these two types of integrals and their inverse Fourier transform will be repeatedly used in the rest of the Fourier optics. So this is now the end of the slide number 28.